I thought I'd throw this slide in just for fun. Is there any more freezing out in our future? After all, we got 4 forces. Maybe we'll have 5 if we have another symmetry breaking. The long-sought Higgs particle is the last piece of the standard model of particle physics. It was discovered about 8 years ago now. The Higgs gives rise to the property that we call mass. It's a quantized Higgs field particle. It's pretty heavy, 126 billion electron volts. That's pretty heavy. Took a long time, a lot of data before the LHC, the Large Hadron Collider, could by random chance have access to energies that big and have maybe seen a Higgs particle, and finally, after a while, the data added up enough, and yep, there it is. But the fact that it's not infinite, or some other value, let's not go off to the wild blue yonder here, may mean the universe is in a false vacuum. It is not yet at the actual true vacuum, the bottommost energy state that the universe could be in. And after all, we do still have a cosmological constant that's an energy density of space itself. So this particular mass is very close to the critical mass whereby in the distant future, when the expansion has cooled sufficiently further, we're already at about 3 degrees Kelvin, but if we go down much, much lower still, we may spontaneously transition to a true vacuum state. And in the process, we would have another inflationary kind of situation, and the forces would all change, and we would just destroy everything at the speed of light. So that would be a massive bummer. But it's still a prospect that's extremely speculative, so I don't know anybody who's actually worried about it. I don't even know of a whole lot of work that's still going into that, but there's probably some people still thinking about it. Don't lose any sleep over it. And you know what? If it happens, you'd never know it anyway, because it goes at the speed of light. So it wouldn't be like in the movies with screaming people and all that. Okay, well, that's a picture of the control room, one of the control rooms in the Large Hadron Collider, I think. Actually, you know what? I'm not sure which collider this is, but anyway, it's one of the big particle colliders. When you look at data from those, then what you're basically seeing is the tracks made through space by the particles that are created by collisions. And you look for collisions, and then you look for the particles that are generated by the energy of those collisions. If they have charge, then they follow curved paths. If they don't have charge, why do they follow curved paths? Because there's very strong magnets nearby, and charged particles moving through a magnetic field, as we talked about, they create curvature. And if they don't, then they would be uncharged. So that's an easy way to tell whether your particles are charged or not. And it looks a lot like fireworks. Now, if you're a real particle physicist, you might look at this and say, wait a minute, Rick, this does... And, okay, you know what? It's a cheat. I admit. I cheated. This really is fireworks. Sorry. It was... I mean, I liked it. It's got color. It's... Anyway. Real particle tracks do sort of look kind of like that. Okay, here's cosmic history back to the first 3 minutes. Okay, back to the first 3 minutes, we have very high confidence that we understand what's going on. Very accessible to the laws of physics that are easily demonstratable in our technology that we have, mastered very well. So today we live in a time with a lumpy universe with stars and galaxies. You go back earlier, the galaxies are denser. Back far enough, earlier, way earlier than the first billion years, then galaxies haven't really formed yet. You just have stars, and then even the stars haven't formed, and if you go back to 300,000 years, it's just hot gas. This is where the microwave anisotropy is visible. The lumps formed in the early universe by the dark matter that we decided is cold dark matter. It must be cold dark matter to have the lumpiness that we see. Then if you go back even earlier, then you're in the era of not atoms but nuclei, and even into the quarks that make up some of the nuclei, and they don't make up electrons, but they make up They make up some of the particles. And you could even have nuclear fusion going on, and if you go back even earlier, well then things get even more different. So you go back even earlier than, now this is the so-called particle era, earlier than the first thousandth of a second, back to the 10 billionth of a second. So particles exist here. And then you go back further and you're in the electroweak era, so you have now unified two of the four forces of nature. And then maybe you go back to the gut era, the grand unified theory, which we don't have yet, but we think, or we hope, might still be out there. And then if you go back far enough, the universe is so hot, the travel time from causally connected places gets so small, you're actually in the total realm of quantum, well, you're back to even before, you're back to a size where the universe is fuzzy even on that scale. And we call that the Planck era. And before that, all of these things cease to have meaning. Okay, you can't talk about photons and particles and anything. You know, at the Planck era, everything dissolves into a quantum fuzz. Now, I think we talked about this before, but this is probably a good time to again try and explain to you where the matter lumps that we see in the cosmic background, where they came from. So the universe really did start, we think, in a quantum state. And that means that the density from place to place to place was not really truly constant, even though nominally it's constant. But because of quantum mechanics, it's only a constant plus or minus this fuzz factor of quantum uncertainty. And so in a very real sense, the density from place to place and moment to moment changes by the amounts allowed by quantum uncertainty principle. Now, as you expand from that, you transition out of the time when you are at the quantum realm into a realm where you're large enough that whatever lumps are still there at that moment, they have now frozen in. This is still very, very, very early, but it's out of the quantum realm now, and forever after, those lumps are frozen in. Now, those lumps were only on the size of the quantum uncertainty principle, way down in the subatomic realm, but now they have been blown up by inflation to finally be galaxy-sized fluctuations in density. And again, those fluctuations are just a reflection of the quantum uncertainty principle. They're literal quantum uncertainty fluctuations frozen in and then expanded to scales big enough that is now frozen into the stuff that came out of the Big Bang itself. Now, the particles that make up matter are charged and feel the electromagnetic and strong forces, and they're way too hot to fall into lumps at this point. But the dark matter doesn't feel any of that. It feels maybe the weak force and nothing else. Not electromagnetism, not the strong force. So the lumps in the dark matter could form right away. And it's the lumps in the dark matter that the gas of hot particles and hydrogen and helium gradually then fell into. Now, after 300,000 years, not much had fallen in. It was still pretty darn hot. But it had fallen in a little bit, and so there is lumpiness in the ordinary matter due to the stronger lumpiness in the dark matter, because the dark matter lumps could form right away, right after the quantum realm. So the lumpiness in the ordinary matter is only about 1 part in 100,000. I mean, it's really, really, really smooth. I mean, it makes homogenized milk look way lumpier by comparison. So when I say lumpy, I don't want your imagination to run off with you. It's really smooth. But it is lumpy to 1 part in 100,000. So that's a little teeny bit of lumpiness. Okay, so here's another way to try and map out the history of the universe. Dark matter produces a density of wrinkles, and then eventually the stable particles are produced, and then those eventually fall in, produce little teeny tiny lumps. Those are visible in the cosmic microwave background, and then after a billion years or so, you get lumpiness big enough to start forming the stars, and then they fall together with the gas around them to make the dark matter and light matter formed giant black holes in the middles of galaxies, and then more stuff falls in around it, and you make disks of galaxies, and you make halos, and eventually you're here, where we are. There's us. Okay, there's your short history of the universe. Here's another history. So you can plot it in terms of time. Now, this is a pretty dramatic log scale, so we're going to go from 10 to the 20th seconds, that's about now. 10 to the 19th seconds or so is now. One with 19 zeros after it, that's a lot of seconds, about 13.7 billion years. And you go back, and of course you don't have to go very far before you're already at the first second of the universe. There's the first second. Everything back here is the first second. Now, we think we know physics pretty well to get back to around here. And even, the weak and electroweak force, we think we understand that. So we got it nailed, we think, pretty well back to about here, 10 to the minus 12 seconds. Going back further, it gets pretty fuzzy. Okay, not just because of quantum fuzziness, but, knowledge fuzziness. We can't probe physics at scales that are this energetic with the equipment that we can afford. Okay, we can't make particle accelerators that can probe down here. So we're left with our smarts and our sense of beauty, and then trying to find maybe out there in the universe itself is the only place where these kind of experiments have been run. And so people are trying to be very clever. This is, in fact, is an idea probably worth mentioning, and that is that there was a time back when I was a kid where particle physics people worried about the very small, and cosmology people worried about the very big. And those two didn't have a whole lot to say to each other. But they've gotten much more cozy together because the particle physics people realize that they've now understood enough that if they're going to get more answers, the only place where it's been done is in the universe itself. And so they're going to have to talk to their cosmology people. And of course we have cosmology people who maybe even came from particle physics backgrounds, and we have cosmology people who have learned particle physics very, very well. So I'm thinking of my old compadre Joel Premack, and another compadre Stefano Profumo, who are in that category. Particle physics people who are very good at understanding cosmology and trying to synthesize the two together. Those are the kind of people who are really going to get this figured out if we ever get it figured out, I think.